So today I'm going to be talking about some work that my co-authors and I at JPL have been doing on improved modeling of the solar radiation pressure for the Block 2F satellites within JPL's background solar SRP model, GSPM13. The basis of our current model is in GSPM04, developed by Yoaz Bar-Seaver and Da Kwong, where the magnitude of the SRP force is represented as a truncated Fourier series as a function of the Earth probe sun angle, or the EPS angle, which is represented in this figure and in the equations as epsilon. So the Fourier coefficients, Sx, Cy, and Cz, are dynamically fit to actual GPS orbit data. Two of these terms, the Sx2 and the Cy1 term, are clearly exhibit a dependence on the beta angle. And so in the talk, I'll be referring to the beta angle dependent terms as those will be Sx2 and Cy1, and the non-beta angle dependent terms will be the other Fourier coefficients. And in the second iteration of the model in GSPM10, these were shown to be best represented with the second order polynomial. And so the three polynomial coefficients, A1, A2, and A3, are fit separately when the beta angle is greater than 0 or when it's less than 0. Our current model is GSPM13, which was a complete reprocessing based on 21 years of JPL final orbit data for all satellite blocks. And one model, or one set of Fourier coefficients, is estimated per satellite block. The main innovation in this model was that the satellites were divided into subgroups within each orbit block. Because it's observed that you actually have variability of the different GPS satellites within the block, so it allows the model to adapt to that inner block variability. And because these Fourier coefficients are estimated from dynamical fits to long reference trajectories, when this model was developed in 2013, we only had sufficient data from two GPS satellites, GPS 62 and 63. And so it's necessary now that we have the full suite of the Block 2F satellites, there's 12 of them, to update the model to be able to separate it into subgroups, as well as to just take into account the increased data strength that we have now. To generate the model, the basic process we follow is we start off with the JPL final orbit products. From those, we generate an initial set of smooth 24-hour orbit files. We do some analysis of the orbit and clock precision and establish some overlap acceptance criteria to ensure that we're getting high-quality data into estimating these parameters. From that, we create multi-day reference trajectories between 5 and 10 days. And then we dynamically fit these SRP, those Fourier coefficients, from the reference trajectories. From the beta-dependent parameters, X2 and CY1, we sort the satellites into subgroups because those are what really show the biggest variation between satellites within the block. And then we estimate those beta-dependent parameters by group. And these last two steps are really an iterative process where we develop a set of groups, we do some validation, and then we can go back through and redo the groupings. So this first set followed pretty much exactly the GSPM13 methodology. Since we were only reprocessing Block 2F satellites, the data set was from June 2010, when the first 2F was launched, up until April of this year. And then the main analysis in this talk is in these last two steps, in looking at the variability of these 2F satellites, sorting them into groups, and iterating on that process. So there's quite a bit of data editing that goes into this, because getting that good base data set to estimate the coefficients is really the most important part of developing the model. So we eliminate periods when the satellites are outgassing, and we do a lot of editing on the reference trajectory arcs. For the 2F model, we used 5-day orbit arcs for particularly the later launch satellites to ensure that we have enough data going into the model. And we also estimate those non-beta angle dependent coefficients for each reference trajectory arc. And then if you look at the scatter of those parameters from the mean at around 1 sigma, you get a real increase in the variation of that scatter. So we only use that first 1 sigma set of arcs in our model. We then sort these satellites into subgroups based upon the fit to the SX2 and the CY1 Fourier coefficients. And these satellite groupings that we develop are really a trade-off between specialization of the model to those different satellite characteristics and also getting enough data strength to get a stable coefficient. So certain satellites that have a lot of data strength and have a really unique profile will perform better when they're grouped independently, and then some satellites where perhaps the SX2 parameter is less stable or they haven't been launched for very long will perform better when they're in groups. So to illustrate this, in the figure you see the SX2 parameter fit for all satellites at once, and then if, for example, you look at an individual satellite, you see a very different shape. So it's much more linear here, whereas before it's a more parabolic shape, and the magnitude of the SX2 parameter can vary quite a bit between satellites. And we can also improve the performance of the model by estimating those non-beta angle dependent parameters by subgroup. Certain subgroups prefer those to be estimated with the entire block of satellites, and certain ones perform better when that's estimated independently. After maybe 21 iterations, we ended up with 7 satellite groups for the Block 2F satellites, between 1 and 3 satellites per group. From the figure, I know it's pretty busy, but the main things I want you to get from it are the overall variation of the magnitude of that SRP force against the EPS angle, as well as that there's 2 main shapes in the new model, which I'm calling GSPM 13B, that are almost out of phase. So if you look at the local maxima and minima around 90 degrees, around half of the groups go up, and then a few of them go down at the local minima at that point. And the previous model, GSPM 13, I should have noted in the following figures, the updated model is called GSPM 13B. So the previous model, GSPM 13, actually does a surprisingly good job of averaging out all of those coefficients, and I'll go into the why a bit more later, but it decently fits the overall variation within the 2F satellites. Our primary performance metric is looking at orbit prediction error. So we do one-day predicts where we fit to the IGS final orbits over a 30-hour arc, and we propagate forward for 1 additional day. And then the 4th day predicts, which are going to have a bit more weight in our analysis because you're capturing some of the longer-term dynamics. We fit to the IGS final orbits over 3 days and then propagate forward for 4 additional days. The error that we're looking at here is going to be the position RMS difference over the final day of that predict arc and the corresponding IGS orbits. We use the IGS orbits to get at least a bit of independence from the data that we use to train the model. And then we also look at the impact on network POD. So we don't expect much variation in the orbit and clock overlap statistics, but obviously any degradation is going to be a red flag. And also if there's any impact on the resolution of phase ambiguities. The one-day orbit prediction error shows a clear improvement. If you look at the histogram, you see that the updated model, GSPM 13B, the entire curve is shifted to the left. And if you separate out this data set by eclipsing arcs and non-eclipsing arcs, I think I forgot to mention earlier that we're only fitting the Fourier coefficients to the non-eclipsing arcs. So naturally we expect better improvement in the non-eclipsing arcs, and we see that we reduce the error by a couple of centimeters, so about an 18% improvement. And then for eclipsing arcs, we still also reduce the error by a couple of centimeters and still get some improvement there. And we see a similar story with the 4-day predicts. The entire curve is again shifted to the left, and we reduce the error for that 4th day predict by about 7 centimeters or 16%. And we still get a bit of an improvement in the eclipsing error. And we're defining also the eclipsing and non-eclipsing arcs with a beta angle of 14.75. And in the eclipsing error statistics, we're also ignoring very low beta angles, so basically with a magnitude less than 1. So the overall view of this shows that we get a decent amount of variation between the improvement in our prediction error. And so between 1% for GPS 71 and then 27% for GPS 70, I believe. Yeah, and it's important to remember that this is the relative improvement. So this is the relative improvement from our previous model. So overall, we see a clear reduction in the mean orbital prediction error, and this is for the 4th day statistics of around 7 centimeters. But the ones that didn't necessarily improve as much may have just not varied very much from our original model. So I mentioned earlier that we only used 62 and 63 in GSPM 13, and we noticed that even though they were the basis for that model, they still both improved by about 12%. But if we look at what those two satellites, they're each actually in their own group, what they look like, you see that they are representative of the two variations that we had in that SRP force as a function of the EPS angle. So it was really a bit by luck that we got the model that fit all of the satellites decently well, but didn't do a particularly great job for any individual satellite. And then in contrast, GPS 70, for example, showed a 27% improvement, but didn't vary that much from the original model. And so this really highlights the sensitivity of these parameters. So GPS 70 was grouped together, especially because it was the most recently launched satellite, with GPS 69 and 73, and both of those showed less of an improvement than GPS 70 did, even though they're all together in the same group. And so the sensitivity of these parameters is something we still want to look a bit more into. In terms of the POD precision, we see very little change in the orbit and clock overlaps. There's a tiny improvement in the orbit overlaps, about 0.3 of a millimeter for both the median and the maximum. And then essentially no change in the clock overlaps, maybe 0.1 of a millimeter improvement in the maximum. So these are positive but almost negligible changes there. We were actually pretty happy with our impact on ambiguity resolution. Even though it's small, you see that we get about 0.1% improvement in that top bin percentage. This is about the same magnitude as we saw with the change from GSPM 10 to GSPM 13, which was an update of the entire constellation of satellites. So this POD was done for the previous 2.5 years, where the Block 2Fs were about 1/3 of the constellation. So even with an update to just that amount, we still see a decent improvement in the ambiguity resolution. All right. So overall, with our updated GSPM 13 model, GSPM 13B, with 7 subgroups of satellites, we're able to better capture the inner block variability, and we improve the fourth day prediction error by 13%, with a slight improvement to the resolution of phase ambiguities, and a negligible but positive impact on the orbit and clock overlaps. And then we also want to investigate looking at a separate model for satellites in eclipse, because as I said, we only fit the Fourier coefficients to the non-eclipsing data, and then also comparison with other SRP models.